Share screen. Okay. Hello, everyone. Welcome to our second neural network workshop. This is part of a 4 or 5 part series. I think it's 5. 5-part series on neural networks. So the topic of today's presentation is going to be all about learning. How do neural networks actually do the process of learning that we kind of hinted at last time, but didn't really go into. I will be co-hosting this presentation with Edward, Catherine, and Stone. And here is our agenda. So our presentation, we're going to start with a review of what we talked about last workshop. And then we'll start to move into gradient descent. We'll talk about why it makes sense, why we even want to do it in the first place. We'll also look at a little bit of math, and then we'll move into backpropagation. And for backpropagation, we'll mostly focus on why and what it's doing. The math is a little bit involved. We will present the equations, but we won't go into the derivations. If you wanted to go even in more depth with those derivations, we put some resources at the end, so you could just go to those and read to your heart's content. Okay. Let's start with the review of the neural network. So last time we introduced the neural network, and it was this architecture where basically you give it an input, and treating it as a black box, you get some sort of prediction or some sort of output, right? In this example here, we're feeding it an image of a dog, and our neural network is supposed to classify what this image is. It's either a dog or a cat, and it's giving probabilities in this case. But really, we can formulate our neural network mathematically as taking an input vector. So an image of our puppy is really just a collection of numbers, and pushing it through this function, a really complicated function, but it's still a function nonetheless, and we get an output vector. And so drawing this out in an actual diagram, I've just put all the numbers in vector into these circles, and these circles represent neurons, or individual units of the neural network. And on the right side, we have the neurons for the output layer. I will refer to the first input as the input layer, and this column as the output layer. And so what's going on with the neural network is, well, we have this input, and we also have these, what we call weights. And all the weights do is they take the, they basically, you take the weight and you multiply it by the input. And then you do this over all the weights and all the inputs, and you basically sum this, right? So it's a weighted sum. And this over here denotes a bias. It's like a weight, but it doesn't depend on the input. Any questions so far? Okay, so basically, you can also kind of think of this as a dot product, right? So if you have your input vector, and if you put all these weights in a vector, then the weighted sum is basically the definition of a dot product, right? So there's a question that says, wait, the dotted circle is bias. Yes, the dotted circle represents bias. This is not like an input. Okay, so one thing I want you to note is that this set of weights and this bias is associated with only this neuron, this output neuron. So basically, we go through calculations, we calculate a number. For example, we just got 3.8. We notice that 3.8 is not really like in our probability range, right? Our probability range is from 0 to 1. So one thing we could do is pass it through this activation function. And this activation function basically just squishes whatever it takes in into that 0 to 1 range, right? So for example, we could get 0.9 after we do that. And for the other output neuron, we have another set of associated weights and another associated bias, right? And so we just go through the dot product again. We multiply -2.3 times 255 plus 1.6 times 75 and so on, and then plus -1 at the end. And then we get some output like -4, passes through our activation function to squish it into 0.1. Any questions? Are the results of the multiplication normalized? No. So the activation function, there's a question on this. So the activation function, the purpose is sort of to change like, well, one of the purposes is to change the codomain, or the range in which your outputs fall under. So before, I'll just go a little before. Before, right, our weighted sum is just -4, right? But we push it through this activation function, and yes, we do scale it down to in the range of 0 to 1. Any more questions? Okay. And we can sort of write this operation as literally how I described it, the dot product of the weight vector and the input plus the bias. And same thing for the other one. And I want to point out that it makes sense that we have a different set of weights and bias for the different output neurons, right? Because you can think of these output neurons as being associated with some sort of category that we're trying to label our data as. So for example, in the first one, we said it was like dog, and then the second one was cat, right? Well, if you think about it, right, each of them is taking in the input, right? Each of them is taking in X, right? But what they're looking for in order to classify it as dog or cat is different, right? Cats and dogs have different features. And so it makes sense that we want to weight them differently. Here I just compressed the equation into one. So this is now a matrix. You can view these as row vectors, and this just becomes a matrix multiplication, and this also becomes a vector. And I'll just write the matrix as W. So f of x is the prediction of the neural network, right? This is f of x. Like, this is what comes out of the neural network. It's actually a vector of 2 numbers. X is the dog. So it's mapping from an image space to this sort of probability distribution. You learned a dot product in, you definitely learned it in linear algebra, so Math 18. You also touched on it briefly at the start of Math 20C. And here I just noted that this is equal. This is literally the output of the neural network. And so in our code, I'm using, or we're going to be using NumPy. And so that's what the NP stands for. It's the NumPy library in Python. And this is basically just translating this calculation into code, right? It's a matrix multiplication of W and X. And then we add our vector B. And then we just pass it into some activation function. And out comes our output vector. And this is another, this is actually in our workshop code. So we have a specific activation function, we call it sigmoid. And we do a dot product because our weight vector is only, there's only one output neuron for our workshop code example. So there's really only one set of weights that we're worried about. And so basically, matrix multiplication of 2 vectors is just the dot product. And you could, the T's stand for transpose. Those just rotate your matrix or vector by 90 degrees. Any questions? Okay. So now we will go into motivation for gradient descent. Edward.
Okay, so I guess after Jason really explained the whole fundamental idea of what a neural network does, I guess now the question is how we essentially train this neural network. And so I guess the first thing we'd have to understand is what a gradient is. So a lot of this stuff is basically just linear algebra stuff. And a majority of what neural networks do is also just based on linear algebra. So I guess the first thing is that we start off with what a gradient is. So a gradient is just like a plane vector pointing in the direction of the steepest slope. So as you can see in that picture, the gradient is like the arrows at the bottom, which shows in which direction the steepest kind of slope is. Like slope in the sense of a 2D graph is basically just like the derivative of the function itself. And that's essentially what the grade is. It's just like a derivative in terms of the point. And so what gradient descent is, it's an algorithm that essentially utilizes the gradient. And the purpose of gradient descent is to just minimize some function by moving the direction of the steepest descent, negative of the gradient. So as we can see in the diagram, the gradient is moving outwards from the function. So what gradient descent does, it actually moves toward goes like into the function. So you can see at like with the mouse, there's like there's like the local minima. And the whole purpose of gradient descent is to try to reach this local minima. And so how does this connect to neural networks? So we can imagine neural networks are just like a really complex function in a really high dimensionality. So a one layer neural network with X neurons can model a function with X plus 1 dimensions. Let's imagine like a simple, because like let's say you have like 2 neurons. And with 2 neurons, there are 4 variables because there's the weight and bias for each of them. And so with the input and also the output, then you just have a really high dimensional function relative to the input. And so what happens is that a vector is basically fed into the network and it would generate a unique vector output that is somewhere on the function, function being the neural network. And the metric and then we need to figure out some metric for optimizing this vector output compared to the actual output. And so this connects back to gradient descent because the value we're trying to optimize and get to is going to be the minimum value. Yeah. So I guess the main takeaway from that is that, yeah, the neural network is just a function and we just want to minimize that function. So to do that, we would first define, let's say, a loss function called L that determines how different the actual output is from the expected output. So if we go back 2 slides and look at that image, let's say the point or the predicted point is like somewhere on the graph. We would calculate the difference between the random point on the graph and also the minimum point, and that would just be the value outputted from our loss function. Yeah. So, and as a result, gradient descent allows us to reach this minima, which is not necessarily global, and we will talk about this issue later on. And so what this minima essentially is, it's the optimal parameters for the neural network based on the loss function L. So as a result, for any input that's given, the difference between the actual output and the expected output would be close to the minima. And there's a meme there. And now I guess it's just like more of like a visual explanation of what goes on there. So let's say we start off like that's the function, that really like cool looking like curvy thingy. So that's the function. And then the cyan point is where we're at the function currently. So this is like the pre-trained neural network, and given some random input, that's the point it gives in this high dimensional space, which is like that cyan point. And then, so for that one, we would have to calculate the gradient of that point, which is on the next slide. So as we can see, the gradient is always horizontal relative to essentially where it is. on the graph of the function. And so we can see that the gradient is pointing outwards. So the direction that we would be doing gradient descent is going to be opposite of that, and it would be going towards the left. And this is kind of like during training, we can just see that the sand dot just slowly goes down, like quote unquote goes down, because it's like going towards the local, like the minimum value. And also another thing we should notice is that the arrow itself is still pointing outwards and to the right, because the gradient is also changing at each iteration. So yeah, so after the loss, after it's being trained, for any given input, the output would be somewhere really close to the minima of the function. So one thing to keep in mind is that this function has one minima. However, some functions have multiple minimas because, well, it's like really curvy and stuff like that. In that case, we would have to figure out specific ways to somehow get to the global minima, and that will be covered in a later workshop. But for the purposes now, we just consider that a little bit of noise is added into the training, such that even if it's at the minima, it could potentially like move around a little bit inside the curve, in the hopes that somehow it's able to go down and gradient descent even further down to find like a lower minima.
First, before we continue, are there any questions about this visual explanation or why we're doing gradient descent at all?
What was the thing about the dot pointing outwards? I thought it would be pointing inwards towards the minimum because that's how the gradient goes.
Yeah, so the gradient of the function is like the direction in which it's changing the most. And in that function, it's actually going outwards, because this function is really similar to the one that we covered really further back, as you can see with that really far back image, which shows like the gradient. Like this is like a really similar function to the previous one. So we know that the gradient is going outwards, and gradient descent goes in the opposite direction of the gradient. So while gradients go towards the right, the gradient descent goes towards the left.
Got it. Okay.
Yeah. And to address Colin's question, it's theoretically possible to reach the global minimum given a large enough training time. But for most purposes, this is unfeasible because it's going to take a really long time to get there. So sometimes it's just really good to just get to like a minimum. Another question is, if gradient is only horizontal, how do we reach the minimum vertically? Because we know that, so I guess the takeaway is that for this one is that the input on so given any input, the output is always going to be on the graph of the neural network. So if the gradient is horizontal, it just knows that it should be going the other way. How should I explain this? Because if it's going horizontal, it means it's going that way. But if you want to not go in horizontal, just go the other way. Yeah. Jason, do you want to add on to this?
Yeah, sure. First, I would probably clarify that. So this curve that you see here, this is actually the loss curve, well, surface, right? So this is the function of actually how bad your neural network is performing, not necessarily the neural network itself, right? And that makes sense because, well, we really don't want our neural network to be bad. We want to find the lowest point, right? The least badness. And so our gradient, you can also think of it, I mean, we put it up here, but really it's a projection from down here. You could think of it as an arrow in this sort of 2D space down here, right? That's what we mean by horizontal, right? And this arrow just points, if we call this space our parameter space, right? So our weights and biases are down here that we can tune. And this vertical axis is our loss. Then all we're doing is we're just pointing an arrow in our parameter space to navigate it, right? And the point on the loss function is basically just, well, that point, like at xy, at z, right? There's another question. Edward, do you want to take it?
Mm-hmm. So it's literally the weights and biases. Generally for neural networks, you generally want to like compress it to between -1 and 1, because doing because in most activation functions, the most significant changes happen between -1 and 1. But for our purposes, we're just like visualizing. We're just trying to like visualize what a neural network is currently. So for temporary purposes, don't assume that they're compressed. They're just like the literal weights and biases values. Like I guess this whole graph thing is just to like try to drive home the point that a neural network is a really high dimensionality function relative in terms of with respect to the loss. So like this is just like a 3D graph, because I don't know how to graph like 4D and stuff like that. Yeah, that's the reason why it's only a 3D graph.
So there's another question. So Z is output from the dot product of the last layer weights and biases. So again, this surface that we have here is the loss. It's not actually the output of the neural network, right? So Z is not equal to f of x, right? Z is actually equal to L. And L is parameterized by the weights and biases of our neural network. Does that make sense? All right, moving forward. So we're going to talk about why gradient descent makes sense. Like, why do we do the gradient, right? Why not some other vector? And to do so, we'll first introduce a loss function. This is just an example loss function. There are different ones out there that are for different purposes. Mean squared error is the one that you see here. And it's most commonly associated with regression. So if you imagine you have a plot of a bunch of points, how can you fit a line through those points that basically fit the data as well, as best as it can, right? And so the way we formulated it here for neural network purpose is we have this input vector, x sup n, and basically we're looking at this difference here, right? And y represents what we want our output to be, right? Like the true value, right? The universal truth for our specific input, right? Like this image of a dog is a dog. And our f here represents our neural network output, which may or may not be correct, right? And so all we're doing is we're just looking at the difference of this, right? And these double bars here just stand for the norm. You can think of it as like Euclidean distance in higher dimensions. So basically just the distance between these two vectors. And basically we square it because if you don't square it, then it's possible to get actually negative values, and those could cancel out to 0 with the positive values. So that's why we square it. And this is summed over all our all our data, right? So n is basically the input number, and we have capital N of those. Yeah, and also this 2 right here, you really can just ignore it. It just makes some of our upcoming calculations a little bit cleaner. There's really no theoretical reason why we have it there. It could be 3 or 4. It really doesn't matter. Any more questions? Value? Yes. So even though these are vectors, the L2 norm here, which is what we call the magnitude, is basically just a number. And so you're summing just a bunch of numbers to get the total loss. Isn't magnitude divided by the vector? So that, no. You're thinking about normalizing the vector, I think, to make it a unit vector. Is that right? Why are we using 1/2? So again, 1/2 is just to make some of the upcoming calculations a little bit cleaner. There's actually literally no theoretical reason why it's there. Like, so you can basically ignore it. Are we basically trying to take the average? Yes, we are. We actually, that's why we have 1/n here, right? Because we're calculating the sort of all these distances for each input, right? But we have a lot of inputs, so we just average that loss. Yes, it is basically the expected difference. Okay. So again, like we formulated our problem as wanting to change our weights and biases so that we're decreasing our loss fastest, right? Why the fastest? Well, why not, right? You don't want to learn slowly, right? You want to be very efficient about how you learn. And so we want to be very conservative about what steps we take and how good those steps are. And so in terms of our graph here, I just copied it over here and kind of labeled some things to make it clearer. Again, this line right here is gradient. So this is sort of the direction of steepest increase in L. L is just our loss function, so how bad our neural network is performing. V is basically the direction that we want to move in our parameter space, right? So in this example, well, we only have 2 parameters, Vi and Vj. So basically what we want to do is we want to nudge Vi and Vj independently in some direction. And a vector V just captures those changes together, right? You can see it in this definition. It's just the collection of all these little nudges to our parameters. So basically, if we want to change our parameters, right? Well, what we're doing is we're updating each parameter by just adding on these little nudges, right? And so that's what's characterized here in this equation, where Vi prime is our new updated parameter. And the big question is, how do we choose V, right? How do we choose which direction to actually move in our parameter space? Or in other words, how much to change each parameter so that our loss is actually decreasing, hopefully not increasing, right? That would be bad. But not just decreasing, but decreasing as fast as possible so that we want to learn efficiently, right? So again, we want V to be in the direction in which L decreases fastest. And so we can sort of motivate, I mean, obviously we've explained in a previous slide that it's, opposite direction of gradient, but we can motivate why that is by sort of estimating how much we actually change L conditioned on which V we pick. And that's captured by this formula here. So delta L is just the change in loss, is approximately equal to, and this stands for the partial derivative. For those of you who've taken 20C, to be familiar. If you haven't, and you've taken calculus, it's just a derivative when there are more than one input variables, right? And you just treat all the other variables as constant. So literally all the same derivative rules apply. And if you haven't taken calculus before, a derivative is just the slope. That's all it is. So basically what we're doing here is we're taking all these partial derivatives and we're multiplying them by the small changes that we make, right? And so what you'll notice is that as these small changes approach partial VI, which again, partial VI is this infinitesimally small nudge in our parameter space, right, with respect to some parameter, right? Like it's literally the smallest possible move you can make, like the atom next to the next atom, right? So as our nudge approaches, gets smaller and smaller, approaches that infinitesimally small nudge, basically these cancel out, right? Like this delta V1 becomes partial V1. It becomes that very small change. And so these effectively just cancel out and you're left with just a change in loss, right? An infinitesimally small change in loss. But that makes sense because now we're just summing these changes in loss, right, with respect to each of the parameters to get the total loss that's changed. Any questions so far? Okay, it's worth keeping in mind that this approximation only holds, again, if our nudges are really small. Like we want it as close as possible to these partials, right? And so, again, we can reformulate our first point in terms of saying, well, we actually want delta L, or change in loss, to be negative, right? Because we want the loss to be decreasing. And we want the absolute value of delta L to be as large as possible. So not only is it decreasing, but it's decreasing the fastest, right? There's a question, is the derivative of the sum? It's actually the dot product, which is what's right here. So if you've taken linear algebra before, you might be familiar with the dot product. If you haven't, it's literally just this, right? V is, again, our little changes. And basically, we take the first element of V, we multiply it by the first element here, and then we just do that for the rest of them and then sum them all together. Another question, so we want delta V1 to approach the smallest possible change, which results in, so this equation, again, is trying to measure how much we change or loss, right? Depending on the direction of V, right? So our goal actually is to it's to pick a V, but our goal is really to do so in a way that accomplishes this, right? L to be really negative and like really the magnitude to be really large. And I pointed out that, so this vector right here is actually just a gradient, right? For those of you who aren't familiar with the gradient, this is literally all it is. This is the definition of a gradient. And this upside down triangle is called nabla, it's a Greek character. Or we just say like gradient of L. And it's literally just this vector. It's just a collection of the partial derivatives. So we could just rewrite our approximation for change loss as just dot product. And so there's this property of, the dot product is also defined as using this equation, right? So if you take it in linear algebra before, it should be familiar. But if you haven't, this basically is the magnitude of the first vector times the magnitude of the second vector, so how long they are, multiplied together, times the cosine of the theta of the angle in between them, right? And you can basically just memorize this equation. Like, there's a geometric reason why it works, but it's not too important right now. let's see, another question. How do we know the size V? Okay, that's a really good question. So obviously we don't want V to be huge, right? Because if V is huge, then you could imagine like V being like all the way over here. We totally miss the bottom of, we totally miss our minimum, right? So again, our approximation is only true for a very small V, right? And like an infinitesimally small V that points in a specific direction, right? But really we can just fix V at some really small size and not even really worry about V for now, or the size of V for now. If gradient tells us direction of V, what's its magnitude? So we haven't made that relationship between a gradient and V yet, but we were about to. We calculate V. Yeah. So basically, as I said before, we fix V at a small size, right? And obviously the gradient is just constant. You evaluate it at a point. So we can't really change anything there. We can't change anything here either because it's fixed, right? So the only thing we can actually vary is the angle in between them, right? If we want to accomplish our reminder here, right? So to accomplish part of our reminder, right, the magnitude of L to be as large as possible, you know, there are sort of two angles that achieve that, right? Because the range of cosine trigonometry, remember, is -1 to 1. So basically the largest and smallest points are at theta equals 0 and 180 degrees, right? But we want our delta L to be negative because we want our loss to be decreasing. So there's only one logical choice, right? It has to be cosine of 180 degrees because that's -1. But if we have cosine of 180 degrees, then what happens is something like here in the upper right corner, right? So we have 180 degrees between our gradient of L and the vector in which we're taking our direction. And what this means is that V is actually in the opposite direction of our gradient, which is exactly what we explained in our first part. And so this is why we want to always move in the direction of the negative gradient, right? Because it maximizes, well, you can also think of it as minimizing like the lowest negative or the lowest possible number, which is very negative for our loss function. And here I just rewrote it in as like an equation. It's just some constant times the gradient. And to really make it explicit that it's negative, we restrict that constant to be positive and put a negative sign in front of it. Okay. All right, any questions so far? Is this related to the directional derivative? Yes, this is. So if you take in 20C, the directional derivative, I believe, is actually literally this. It's your gradient and the dot product of some vector, right? The vector that you're taking the derivative with respect to. Okay, that's great. We found what our V should be, or we've explained that it should be the negative gradient, so there's some scale of that. And so what that means is that, you know, from earlier we had this equation where we said our new parameter is just our old one plus a small nudge. We found our small nudge. Here I'm just taking a specific element in our gradient vector that corresponds to parameter I. So it's basically the same thing as before, just a small component of it. And this is basically our update rule. This is how we're updating our parameters. For either it's your weight or your bias, this is what happens. And this symbol here is called eta. It's called the learning rate. So basically it's the rate at which we learn. But geometrically, you can think of it as like how big this vector V is, right? How big this red vector is. And again, we don't want it to be huge, because then we're going to overshoot and miss our minimum. But if it's too small, then it's going to take so long to get to our minimum. So really, it's up to you. You know, eta is called a hyperparameter, which is a number that you are supposed to manually configure, right? And you basically just experiment with some different values for eta and see which one is best for your purposes. Okay. But now the question is, well, how do we actually find this derivative, right? And I go through an example here. I'm not going to spend too much time on it, but basically I have this example neural network, and it's a very simple one. There's pretty much no activation. It's just the identity function, and we want to take the derivative with respect to a certain weight, right? And so basically, that's just the derivative of our loss function with respect to the weight. Here's our friendly loss function we've seen before. And if you remember your derivative rules, we just bring the 2 down here. This is why the 2 is in the denominator, because when we take the derivative, it actually cancels out and looks nice. That's literally all the reason why 2 was there. But basically, we just apply our derivative rules, right? So we take the 2, we bring down here, we multiply by derivative of the inside. Derivative of the inside. So this is, remember, our universal truth. It's just a constant, right? It doesn't change. So our universal truth. So derivative constant is 0, so it goes away. And I brought out this negative sign here, so these are reversed. And basically, f, as you remember, is the activation function of this dot product and bias sum. I moved it back up here. And so, again, through a chain rule, we take the derivative of our activation function with respect to z is just denoting whatever's inside here. I mentioned that up here. So then we take the derivative of whatever's inside there, respect to wj. Dot product, you can think of it as, again, the weighted sum. And you take the derivative of this. This is only, so if wi is not equal to wj, or if I is not equal to j, then the derivative of that is 0, right? Because it doesn't depend on wj. So basically, the only thing that comes out of here, and b is just a constant, the only thing that comes out of here is xn of j. And that is basically our derivative. And so basically, we take that derivative, and then we just pop it back into our formula for updating, right? And that's what we've done here. And as an exercise, you can go home and look at these slides again and do it for the bias. And the thing to note is that this is just for one step, right? One step in our training. We call each step an epoch. And so obviously, we're not going to get perfect results on our first epoch. We basically want to go for k epochs, which is another hyperparameter. So you're going to have to experiment with different k's. And another thing to note is that we're training over basically all our examples, right? If we have n examples in our training set, we're basically training over everything, right? And if you have a huge data set, that might not be practical. So there is a modification to this algorithm, and it's called stochastic gradient descent, where instead of looking at everything, we're only looking at a small sample, right? We're sampling some a subset of our input, like input collection, and basically calculating an approximation of the gradient, right? The approximation because we're not looking at everything, we're only just looking at a sample. Okay. And I also want to throw in a disclaimer that the example we had on the slide for deriving, the derivative, it is of a super simple neural network, right? And as you add more complicated things into it, taking a derivative becomes more involved. And I also want to point out that in this workshop, in our code at the end, we're using a different loss function. It's called cross entropy. And the activation function we're using is something called sigmoid. And so because we're using different ones, like that formula you just saw like 2 slides ago, isn't going to work, right? Because these are different formulas and they're going to have a different derivative. All right, any more questions? how are the original values of the weights and biases chosen? That's a good question. So you can initialize them randomly. So it actually does matter how you initialize them. If you initialize them in a way that like your initial outputs are going to be like super, super large, or like super, super far away from where you want to be, then it's going to take forever to move back to where you need to be, right? So usually what you do is you basically use like a random number generator in Python. You can model your weights as being sampled from a Gaussian distribution, just the normal distribution, like mean 0, standard deviation 1. Just sample your weights and biases from there. Okay, so I want to go over to motivation for backpropagation now. So as we recall before, this is a very simple neural network. It has an input layer and an output layer, and we describe the output as being this formula. And so one thing that we hinted at in our first workshop was that you can have multiple layers, right? You don't have to just have an input and an output layer, right? You can have layers in between. And those layers in between are called hidden layers. And so, for example, how that would affect our diagram here is that we would have these really two different matrices of weights, right? Because in each matrix, we have already a collection of vectors, right? So we have these two different matrices for each layer. And we also have biases. And of course, these biases are going to be different for each layer. And so our formula for the output of f of x is going to look similar to what we saw for our previous neural network. But not what's going inside our activation function is different, right? Now we're looking at the activation from this layer. We're taking the matrix multiplication of that with W2, and then we're just adding the bias of the final layer, right? Basically the same thing as we did before, pretending that this doesn't exist. But of course, our activation in previous layer is actually just, it's calculated somehow, right? And the way it's calculated is, well, the activation of the matrix multiplication of the first layer's weights and the input vector, plus the first layer's bias. This is basically A1. Any questions? And so now we have two hidden layers, right? So now we have three sets of weights. We have three sets of bias vectors. Basically, this is our formula for this final layer. Now we have, a third weight, second activation, and basically we can expand it just as we did before. This is the activation from the second layer. And then from the second layer, we also expanded it, and it was this, right? Basically, there's this sort of almost like a recursive definition going on, right? It's defined in terms of the activation from the previous layers. Okay. So here's where we get into why backprop, right? And what it even is, right? So what you'll notice is that this equation is starting to get very long, right? So, you can imagine like you had like 100 layers, right? You'd have like 100 of these A's and like 100 of these W's and like, 100 B's, right? It would be this absolutely massive, long, just huge formula, right? And if you try to take the derivative of that, right, for, our update learning rule, then you could imagine that, with calculus, that's going to be a really long chain rule, right? So you imagine like if you took a derivative with respect to a certain weight, for example, here I have weight in layer L going from neuron K to neuron J. It's the one in red, right? If I took the derivative of this with respect to that specific weight, you know, for a weight in this layer that's towards the end, it actually isn't so bad, right? Like you might think, oh no, a huge chain rule, but really what happens is that the chain rule doesn't go very far for this case. Because if you're looking at only this weight and, you know, some weight very close to the end, right? Then if you take the derivative, you know, you can imagine like, oh, you know, partial A with respect to everything inside times the derivative of everything inside, and then you basically repeat. But once you get to a certain point, for example, like, you know, this activation, the activation of the previous layer, that activation doesn't depend on the weight we're looking at here, right? And actually, none of the previous layers depend on that weight, right? Because they all come before that computation, right? So if like none of like wjk of L doesn't appear anywhere before here. And so if we take the derivative of all that computation before this layer L, right? But none of that stuff before layer L depends on wjk, then that's just a constant, right? Like you don't have to worry about taking derivatives, doing some complex algebra. It's literally just a constant. You can treat it as a constant, right? And because of that, our chain rule just stops, right? Like we can just say everything else is constant, we're done. And so for weights very close to the end, you know, we don't have a huge nightmare. Any questions so far? Okay. But you know, that was for the case where your weight is very close to the end. What about a weight that's very close to the beginning, right? Well, okay, let's think about it. You have to do the chain rule, right? And so what do? Well, we do like partial A with respect to that weight, and then, you know, we times partial A of this one with respect to the weight, and partial A, and then we keep going and going, right? Because all of these activations depend on that weight, right? And I've shown that in this diagram, right? So this weight right here, the value of it actually gets propagated forward through the network, right? Like this output obviously depends on this weight because we just multiplied it by something, right? And a result came in here, right? But this value also gets used by this neuron and this neuron and this neuron, and pretty much everything that is these dotted red lines, right? Like they all depend on this calculation right here. So if we take the derivative with respect to that weight, well then obviously our chain rule is going to apply here, right? Because they all do depend on that weight. And so now we have this massive chain rule, right? That goes through all these layers. You know, you can think of like 100-layer neural network. That's a massive chain rule, right? And that's super expensive to compute directly, right? If you said, hey, what's the derivative of my loss function with respect to this weight at the first layer in my million-layer neural network, right? Well, to compute that directly, to ask that very specific question, is super expensive. It's going to take like forever to calculate, right? And so here is where the insight of backpropagation comes into play. You know, we talked about this expensive computation, huge, long chain rule that we have to compute. But the first question we have to ask ourselves is, well, when we're computing these chain rules, do we actually have to calculate or compute the entire chain rule each time? Are there some repeated computations in the chain rule that show up in many different places that, you know, we've just memorized and don't need to recompute? And so it turns out there is, right? It turns out if you do the math, you get a lot of repeating chains, right? Or parts of the chains, right? And to show that visually, you know, why might that be? say we're taking the derivative with respect to two different weights, right? They're in different layers, they're different weights, right? And the thing that they share in common when we're computing derivative with respect to them is these lines in purple. So in red, I have what basically the neurons that depend on JK from layer L. And so purple includes red. Like purple is basically the sum of red and blue. It means both red and blue. Right? And blue obviously is the other weight. It becomes purple because these are also red. And then the last layer is just completely purple. Right? Any questions on that visualization? And so what this is actually showing us is that these things in purple, these are shared computation actually. Or at least it turns out that there are shared computations, like literally the exact same thing you're computing if you're computing derivative with respect to this and derivative with respect to this, right? Because the same things depend on these two different variables in the further layers, when you actually do the chain rule, they actually start to become very similar, right? Like parts of the chain rule are literally the same. It only gets very different when you go further into the chain rule, and then that's where you get closer to these, and that's where things start to change, right? But way out here, things are actually the same. And so, you know, just to clarify, those, when we say shared computations, we don't actually mean the derivative loss with respect to some future parameter, right? We just mean that shared part of the chain rule, right? That shared component that was calculated in order to compute the partial derivative. Right, so they're just parts of chain rules that are repeated over and over again across different weights. And so the insight of backprop is that we can memorize those computations, right? Like if there's no need to just recompute something if you've already seen it once, right? Like if part of our product in our chain rule is literally the same value, then if we said, oh yeah, I've seen that before, here's the value, we save a ton of computational resource in not needing to recompute it. So that's what we mean by memwise. If you've, well, I'll get to that later. Let me move this down. Okay. And so this is what backprop basically is, right? Because the earlier layers have these shared computations based on the future layers, you know, these things are purple. Well, then it makes sense to start computing things from our later layers, right? And then work our way backwards, right? Something depends on a future layer. You need to compute that thing in the future first, and then you can compute the thing in an earlier layer, right? So basically, our strategy is to start computing the actual, yes, the partial derivative of the loss with respect to our parameters here, right? But while we're doing that, in the process of computing that, we save some of these computations that we know we're going to use later on, you know, in more complicated chain rules, right? And in Python, you could think of this as saving them into a dictionary, right? Like this is computation from this layer for this neuron or whatever, and you just say you index into that dictionary and use that value, right? Yeah, so if you've taken CSC 101, this is going to blow your mind if you've taken CSC 101. This is literally dynamic programming, right? Because it's similar to calculating Fibonacci, if you remember, because if you draw the tree out for Fibonacci, you get a lot of repeated computations. And so that search space becomes exponential, right? But by memorizing some of these values, we can effectively get like this linear time computation for Fibonacci. And that's basically what's going on here, right? We basically get this linear time computation, linear in terms of numbers of layers. Okay. And this is just saying what I said before. Any questions so far? Okay. So brief disclaimer, you might be asking, well, what are exactly those shared computations that are the same? Like, can we write it down mathematically? Yes, you can, and we will show you that, but they're gonna look kind of complicated. And I mean, really, they're like, if you sit down and think about it, it's not too complicated, but we're not actually gonna derive the equations because that's kind of involved. But we encourage you, if you're really interested in how these equations came to be, there are excellent resources out there. One that I personally recommend and one that helped me get started was 3 Blue 1 Brown series, and this corresponding online book that he recommends. Super helpful stuff. It explains things very, very well. So here's a scary math slide, right? This is backpropagation. But it's not too scary, right? Let me calm your nerves a little bit. So one thing I want to point out for you 101 peeps is if you look at these two equations, these first two equations, this is actually a recurrence relation, right? We're saying, we're just giving a variable name for this, right? This is the case for our last layer. I said H for our final layer. And for everything before final layer, we have this formula. But this formula depends on, this is delta L. This depends on delta L plus 1, right? So it's literally defined recursively, where this is your base case, right? And this is your recursive case. And so for dynamic programming people, it makes sense to first compute this base case and then work our way backwards. So we're iterating from the H down to 1. And the question, so we're storing them in matrices. Yes, that's exactly what's going on. Yeah, we literally, like this, for example, is a vector. We literally just state that vector, right? Like we create a dictionary that maps from, some way you can assign keys to this to that vector. Okay. Yeah, and so, I mean, this might seem scary, but really, if you break it down, it's not too bad. These are what we are super interested in. These are directly how we change our weights and biases. And it's really just, this is the activation. It's just a real number, a single number. Times, this is also a single number, right? But it's a specific component of our vector. That's why we don't have the arrow up here and we have the subscript J. And really, this all is just derived from the chain rule. These are the repeated computations in the chain rule, just formulated as a vector, which is why it looks kind of scary, right? But if instead you only wanted the one for this specific weight, then things start to look a little more familiar. So I encourage you to sort of go through 3 Blue 1 Brown series as well as the corresponding book and really try to work it out yourself. It's a bit involved. It takes some time, and I stared at it for like a few weeks, and eventually I got it. But once you get it, I think it's really rewarding. It's really rewarding once you see how this is sort of derived. So the circle symbol is the Hadamard product. This is not something that was taught in Math 18, at least in my experience. But it's super simple. It's defined here. It's basically the element-wise product of two vectors or a matrix. I just put a vector here because that's all we're working with, but it's also defined for matrices. Any last questions on the backprop equations before I move on? Okay, so this was sort of the big breakthrough that made it possible for really, really big models, really huge neural networks with billions of millions of weights and biases, super large amount of layers, made it possible for these massive models to become practical, right? Because at some point in I think the 1980s, There's people that are saying, oh, if you have a bunch of layers, it's just not possible. We don't know a rule for, learning things efficiently. And then some people started to discover, actually, no, you can. You do have this rule. You have something called back-prop, right? And, maybe they realized it in a similar intuition that we represented now, or maybe they realized it in some other intuition. But, this was sort of the groundbreaking aha moment of how do we actually make these computationally more efficient, right? How do we make these practical, right? We're not computing things over and over and over again unnecessarily. That makes this super slow, right? Instead, we do it in a smart way that makes this like basically much faster. Okay, and if you want to look at this, we'll release the slides after. You can take a look. These equations are also found in the online book that's linked at the end. They're written differently. I basically rewrote them for our workshop to follow the notation that we used in the rest of our workshop. So you'll see slightly different notation, but really they're the same thing. Okay, so now Catherine, I think, is going to take over for the code implementation. Catherine,
Yeah.
Okay, great.
Yeah, I'm here.
Can you share your screen?
Oh no, it's okay. You can just keep sharing your screen.
Oh, I actually don't have it set up. Do you?
Oh no, it's fine. It's just on the slides.
Okay. I'll reshare.
Yeah. Hello. Okay. I'm Catherine, and I'll be going over briefly what the code implementation looks like. So just a reminder, this is what our initial network will look like before backpropagation. So this is when we've already calculated the feed-forward values, and now we want to use that value to update our weights using backpropagation. So first, we'll calculate our gradient using layer 2, since we'll start from the back and work our way to the front. And then we'll also calculate the gradient for layer 1. And this is just for a very simple neural network. So next slide. So L prime is just calculating the gradients. Just key distinction, when they say backpropagation, they still mean like the calculation of the gradients. And gradient descent means more usually towards what is being updated. So whether you use backpropagation or not, the weights will always be updated in any like model training process. So here we're calculating our gradient for our weight number 2 and getting first we're calculating the feed forward networks or feed forward values, and then we'll get our gradients for layer 1, so W2 and bias 2, and then layer 2 weights 2 and weights or bias 2, and then layer 1. You using weights 1 and bias 1. So next slide. And then this is the process that's going to be consistent across all model training. So since you want to move away from the direction of the gradient to minimize your loss function, you are going to subtract the value, the update value from your current weight, and then that will lead you to a new weight. And then after that, you will keep calculating a feed forward value, and then hopefully that will get you closer to your desired value and reduce your loss. So now I'll have like a kind of example to kind of step through like what an epoch will look like when we run backpropagation. So next slide. So this is how we'll initialize our weights. there's like Jason said, there's like many ways you can initialize your weights, and we'll be talking about this in a different workshop. You can also initialize your weights based on, you know, the mean and standard deviation of your data set. So just keep that in mind. Okay, next slide. And this is what will look like after we calculate the feed-forward values, and then we'll start by calculating, for example, these will be, let's say these are our biases. We'll find the gradient of our first neuron and then multiply that by the value or the weight value in our bias. And then keep going. And then we'll continue to build in our layer 1 and also calculate the back-propagated values or biases for there. So next slide. And then that finishes one epoch. So I've kind of skipped over this, but after we've back-propagated the values, we also update the weights. This isn't changed here, but let's pretend that that is changed. And then we'll continue to do the same process in our next epoch. So we'll update our biases in layer 2 and then update our biases in layer 1. Next slide. And then, yeah, hopefully after each epoch, you will change, the values in your weights will change. And then after you've completely finished training, you'll have a new set of weight values that are completely different from your original value. So next slide. So just keep in mind that if we had a much larger network that has more than, you know, I think the 5 neurons we had earlier, calculating the back-propagated values would be very, very tedious, which is why we, you know, typical machine learning researchers and engineers tend not to implement everything from scratch. So this is the part where I just want to connect pieces to maybe things that you've seen like TensorFlow. Oh, this is PyTorch, actually. Maybe things that you've seen in PyTorch tutorials and just like explain that. So on the left, we have our like implemented code from scratch. And then on the right, we have code in PyTorch. And this is just code for a simple object class, this is like an MNIST classifier. So, you know, first you would set your values to 0. So set your gradients to 0. And then next slide. And then you would calculate the feed-forward values. So net is basically a model architecture that's defined before. In PyTorch, you can define that. You can like define that to be like some sort of architecture that they have or create your own. But here in ours, we made it very simple. We just calculated the feed-forward values using matrix multiplication, and that is the simplest way that you can calculate feed-forward values. Next slide. Oh, sorry, go back. Yeah, so also, okay, I guess this is kind of being covered, but the loss is also being calculated. And then loss.backward is where you're doing the back propagation. So that's what's happening under the hood. And then when you step into your optimizer, that updates your weights. So question, yeah, libraries basically do all this for you, but you know, a lot of the issues in debugging, like, you know, machine learning debugging is very different from software engineering debugging, and like sometimes there's no useful error message to be able to debug certain things. Like, oh, if your model is shoot, I kind of forgot the word. What is it? Like overfitting. If your model overfits, you kind of need to understand that from intuition and like knowing general theory rather than, you know, just like printing things. or maybe you can still print things if you're a god, but generally the reason why we want to have the foundations by like implementing the code from scratch is because it makes it easier to debug when you do actual research, since once you know that what's going on under the hood. Is it useful to learn both PyTorch or TensorFlow, or just stick to one? Yeah, I don't know. Like, I've heard various things from people in industry. Like, okay, on one hand, I've heard that only Google uses TensorFlow and PyTorch is more common in industry. Like, I know Lyft uses PyTorch for sure. But yeah, I don't know. I think it's just personal preference. I like PyTorch, but TensorFlow plus Keras is also pretty like equal. Okay, yeah, next slide.
Great.
Oh,
So,
also, I believe Tesla uses PyTorch. Wait, I'm not sure though. Go ahead.
yeah, no worries. So yeah, we're actually at the end of our workshop. And so now we want to open it up to the audience here. If you have any questions, feel free to put in the chat or unmute your mic. If you don't, then you're free to go. Thank you for coming.
Yeah, so Tesla does use PyTorch. So
Oh,
I don't know. Yeah. There's also, okay, I don't understand this as much, but like there's a lot of like debate between whether TensorFlow or usually the argument for why PyTorch is better is because of like because they have a non-static graph. I don't know what the pros or cons of that are, but that's like the argument that I hear a lot.
So I have a question.
Mhm.
Like after the part where you talked about the gradient, I kind of like lost or like didn't understand it. So do you have any like like way back kind of? I guess number 4.
Number 4? Okay, we'll go back there.
Yeah, I feel bad, but
Here?
no, I think even before that, I like.
See, we're at 5. Should probably go back to 4.
Oh yeah, right there.
Here?
Next one.
Oh.
The next one after that, yeah. Yeah, I think that was the part where I started like kind of not understanding it. So is there something that like I should know at this point?
So what part of it is confusing? Is it like a specific equation, or is it just like everything?
I guess the equation with the y x n minus f, and then you add them up all together. Is that what?
Yeah.
Is happening?
So you don't understand like what's going on here?
Yeah.
Okay. So one thing you could do to simplify this, we actually have a more simple equation over here. So if you just look at this part, this is basically the same as what was on before, just without the vertical bars. Would you agree?
Yeah.
Yeah. And so the vertical bars signify that you're working with vectors. So your output of y is a vector, your output of f is a vector. You're doing vector space subtraction, right? Here we simplify it and say, forget vectors. Let's just work with numbers, like regular numbers. So it might be more helpful to think about this equation first. And so what this equation is doing, you can think about y of x sup n as, for example, replace it with a value t that stands for truth. This is like the true value, right? Or your teaching value, what it should be, right? And f of x of n is like your prediction. So some people denote prediction with a little hat, like a little caret at the top, or they say like y hat. Here we just say f, right? But really it's just the output of your neural network, which may be completely off, right? You don't know, right? And so the purpose of this whole equation is to actually say, well, how off are we, right? And if you ignore the summation for now, right, and you just look at a specific n, for example, n equals 1, that's your first image in your training set, for example, right? Then, you know, again, just looking at what's here, not the sum, what you're doing is you have this truth value, right? This is what your image should be. And you're just subtracting it from what your neural network thinks it's supposed to be, right? And so there's this difference, which is basically an error, right? Like this is how off we are from, like how far away from the truth value our neural network is. Does that make sense?
And then you're squaring it because...
So we're squaring it because imagine if it wasn't squared. So the values you would get in here could be positive, could be negative, right? Like this could overshoot or undershoot, you know, the delta between them could be positive or negative. And the reason why that's problematic is because it's more of a problem when you sum it over many examples. If you have some that's like negative and, you know, another, you know, training example that's positive, right? There's a very real risk that once you sum everything together, those positive and negatives add up to 0. And that's a really big problem because obviously our, you know, our loss shouldn't be 0, right? Like if things are off, right, then we don't want to say, oh, loss equals 0. We have perfect neural network, right? So we square it to force everything to be positive. And that way we can actually like really measure what's going on.
Okay. And then the 1/2n part, that's just like a scaling factor, or? Yeah,
so mean squared error is actually defined as pretty much the same thing without the 2, right? Because it's just an average. You can think of it as an average over all these examples. And the 2, the reason why we had 2 is actually because, actually in this step right here, the second step, you'll note that when we take the derivative of this quantity, that's squared, well, with our derivative rules, this 2 comes down, right? This 2 comes down over here.
Oh, yeah.
And so the 2's just cancel, right? And we just get a nice thing that doesn't have a 2 in the front. That's pretty much all the 2 is there for.
Oh, okay.
Yeah, there's like no theoretical reason why it's there. It could be like 3 or 4 for all I know, but it just makes the derivative look nice. Okay. Any more questions? Okay, we are at our final minute.
Oh yeah, so next week our workshop is going to be on architecture. So yeah, stay tuned for that. So we'll be discussing what's the difference between CNNs, RNNs, LSTMs, and what else? Are you working on that too, Jason?
No, I think I'm on vacation for a while from these workshops.
Nice.
All right, great. Thanks everyone for coming.
Thank you.